Now we introduce the maximum flow minimum cut theorem. So the scenario is a transportation network where you've got an unlimited amount of resources that flow from the source, denoted by an S, to the sink, denoted by a T. And it's essentially a transportation problem. How much stuff can you get from S to T along these edges by transporting the resource along these edges? These numbers here represent the capacity, or the amount you can push along that edge. A flow is any allocation of resources to these edges, subject to two restrictions. One, the amount you push in must equal the amount you push out, except at the source and the sink. That is to say, at vertices such as this, if you push 10 units in, you need to push 10 units out. You can't store anything at the vertex. Everything that goes in must come out again, with the exceptions of the source and the sink. And the other restriction is that the amount you push along an edge is somewhere between 0 and the capacity. You can't have negative allocations, and you can't exceed the capacity of the edge. So, a transportation problem. The objective is to get the best possible flow. And you start by playing the game. You just try. You just have a go at making a flow. So let's try and push some of this across. Just trial and error to begin with, and we later on learn how to validate that trial and prove that it is maximal. So first of all, I'll try and push 10 down here, so I'll just denote that with a 10. If I push 10 in, then I need to push 10 out, so I can put 5 down here, get it to the sink, and the other 5 has to go down this edge. Okay. I can also push 5 down this edge, so right up to the maximum capacity there, and 10 is going in, which means I can put 10 out, and I think that's pretty good. I think that's a pretty good flow. If you're trying this at home, you might also get a value of 15, but there's nothing that tells you that it's maximal yet. It's just pretty good. But at this stage, we don't know. Maybe there's a better flow. Maybe someone can get a flow of 16. We don't know if 15 is the best possible yet. Let's play a different game. I'll introduce the notion of a cut. A cut is a selection of edges whose removal separates the source from the sink. So you select some edges, and the removal of those edges will completely disconnect the source from the sink. The value of the cut is considered to be the capacities, not the flows. Ignore the flows. The capacities of the edges in that cut. So let's make a sample selection, shall we? This cut. Think about the cut as a fence, completely encircling the source. Now, the cut indicates that this edge here that it crosses is selected, and this edge here that it crosses is also selected. And the value of the cut is then 10 plus 5, which is 15. So that's one cut. Now consider a different cut. Let's have a look at this one. No, not like that. Like this. This cut. The edge here with capacity 10 is included. The edge here with capacity 10 is included, but this edge is not included. You see, removing this edge does not separate the source from the sink. It's flowing the wrong way. So whenever you're making a cut, be sure that you've got a sink side and a sink side and a source side. And the source of the edges has to be on the source side. This edge, the source of this edge is on the wrong side. Its tip is on the source side. The source has to be on the source side. So keep the source with the source. This edge and this edge are included. This edge is not included. It points the wrong way. Removing this edge does not further disconnect the source from the sink. Only removing that edge and that edge disconnects the source from the sink. You can leave that one in. So the value of this cut is 20, not 35. And now we come to the max flow min cut theorem. The theorem states that if the value of a flow, that is the amount of stuff you can transport from source to sink, is equal to the value of the cut, then you get two pieces of information. One, the flow is the best possible flow. It's the maximum flow. There is no better flow. Two, the cut you made is the minimal possible cut. There are no smaller cuts. This is very useful. Typically you have one of these things and you want to validate that it is maximal or minimal, so you look at the other. In our example, we considered this network and we came up with, through trial and error, a flow of 15, and we felt that 15 was pretty good. But now we're in a position to prove that it is maximal. How? Cut. Cut with a capacity of 15. 10 plus 5. The fact that we can cut with the same value that we flowed tells us that that flow we had is the best flow. It's the maximal flow. Thank you very much, max flow min cut theorem. As a final example, let's consider the following network. Of course, we have a source, we have a sink, and we want to know how much can we flow from the source to the sink. So we're interested in a flow, and then we're interested in proving that flow is maximal. You begin with just trying to shove as much as you can from the source to the sink. So if I'm looking here at an 11, well, okay, I'll try and put 11 down there, and then oh no, I can only get 5 down here. So maybe and then 2 down here, and so maybe I can't really put 11 down there. Maybe I can only put 7. And then I look further down and I see, oh, okay, so if I put 5 in there, then I can get 3 out here and 2 out here. But if I put 2 down there, then I can only get 1 in here. So really, I can't put 2 down there after all. I can only get 1. And so that 5 is actually a 4. And so I can really only get 6 down here. Okay, and oh, but if I can also put 5 down there. So maybe I can put 11 down there. So 11, there's a 5, and then 5 can keep going. Oh, but then it gets stuck here. So that has to be a 4, which means I subtract 1. So that's a 4, and that's a 4, and that's 10. And that 4, well, I can get the 4 along here, and I think that's it. I can't shove any more. Like I can't shove any more down here because I'll just get stuck by the 4. So I don't use this at all. I don't use that at all. I don't use that at all. Empty, empty, and this is my network. So I'm just feeling that my flow is actually, now let's see. Oh, I did use that one that had a 5 coming through. So my flow here is 10. And I've got a pretty good feeling that my maximum flow is 10 because get out my cutting pen and I try and make a cut. Now when you've got a flow, you only need to look at the edges which are at capacity. They're the ones which you'll end up making your cut. So here, these edges are at capacity, these edges are at capacity, these edges are at capacity, these ones are at capacity. And it's at these ones that I should be looking to make my cut. Sometimes you won't need all of them, but you'll be looking to cut through only edges that are at capacity, as few of them as you can. And in this case, I have to use all of them because my cut is this. Maybe I'll do it in orange. My cut goes like this. You can see that it is a cut because I'm going to kind of completely encircle the source. And so this separates the source from the sink. The edges that are in the cut, well, this one, source is on the source side. This edge, source is on the source side. This edge, source is on the source side. And this edge, source is on the source side. So I count all these edges and I count the capacities, 4, 6, 9, 10. Because my The flow is maximal because this flow, this candidate flow, which I thought was pretty good, is maximal because my cut has capacity 10. Thank you very much, max flow mean cut theorem, again, for showing us that this flow, which I thought was good, is actually not just good, it's the best.